So I realize the title of this screencast is the conversion of alcohols to alkyl halides. And that's what we're going to talk about. We're going to talk about two different ways to do that. But at the beginning here, we are going to talk about the dehydration of alcohols using phosphorus oxychloride. So if you remember, we did the dehydration of alcohols using a strong acid in a previous screencast. And this doesn't always work for some organic compounds because some organic compounds decompose in the presence of strong acids, and so chemists have developed other methods to convert alcohols to alkenes. And so a really common method is to use phosphorus oxychloride, which is shown here, and pyridine, which is an amine base, in place of a strong acid like sulfuric acid. And so this will go from an alcohol functional group to an alkene functional group. Now, that phosphorus oxychloride serves much the same role as the strong acid does in acid catalyzed dehydration. It converts the poor leaving group, which is the OH here, into a good leaving group, and then dehydration proceeds through an E2 mechanism. And we are going to look at the mechanism of this reaction. So when we look at this mechanism, we start with our friendly alcohol, and then we have our POCl3, the structure of which looks like this. Okay, now there are 6 lone pairs around each of these chlorines, but as a shortcut we don't show those. Okay, so we are going to come here, and the first step is that the electrons on this oxygen are going to come and they are going to attack that phosphorus. Right? When they do that, one of the chlorines leaves. And so we draw our product here. And remember, we're following those arrows. Okay, so now we have a protonated oxygen, and here's where pyridine comes in. Now, pyridine is an amine base, and so what that amine base will do is it will come and it will steal that proton, and then those electrons will go onto the oxygen. And so what happens then is we end up with this molecule. Now, right, this is a very good leaving group, okay? And so now this can go through that E2 reaction where you have to look and you have to remember, hey, look, there's a proton there, and then the pyridine will come by and react again. And steal that proton. When it steals that proton, these electrons go there, and then those electrons pop off. And so that's the E2 mechanism. So it undergoes the E2 mechanism, and we end up with our double bond there. Now, there's some kind of nice things here. There are no rearrangements. Because there is no carbocation that forms. So remember, every time a carbocation forms, we have to look for a rearrangement. And there's not one here. So that's kind of a bonus for us as we're trying to predict these products. So at this point, we've learned about 2 reagents for alcohol dehydration. A strong acid like sulfuric acid, or POCl3 and pyridine. the reason it's helpful to have two different methods to kind of do the same thing, go from an alcohol to an alkene, is it's hard to know which one to use ahead of time. So both of these methods used, and so I wanted to show you these methods in natural product synthesis. So if you were trying to synthesize vitamin A and this was your precursor, right, then a strong acid is what is used here. But here, this is where we're trying to make patchouli, and here we see POCl3 being used. So both of these are used in natural product synthesis. Now, alcohols can also be converted to alkyl halides, and that's what we're going to spend the rest of our time talking about in this screencast. So when we talk about the conversion of alcohols to alkyl halides, it's important to remember that substitution reactions do not occur with alcohols unless the OH here is converted into a good leaving group. So what do we mean by this? If I were to take this and just react with Cl-, this reaction is not going to occur, okay? I have to take and use the acid component of the Cl, like HCl, for this reaction to occur and form the alkyl halide. The reason this won't work is because the OH is a poor leaving group. The HCl will come in here and protonate this, and then we'll have a good leaving group. Now, here are two examples of how you would see these reactions set up. This is a general method to prepare either primary, secondary, or tertiary alkyl halides. So we can see a primary example here and a tertiary example here. More substituted alcohols usually react more rapidly with the acid there. And so what we find is the tertiary alkyl halides tend to react the fastest compared to the secondary and primary. So how does a reaction of an alcohol with a acid usually occur? Okay, well, when we look at this, the first step here is a proton transfer step. Now, this is an acid-base reaction. That proton transfer is very fast, right? And so, right, that strong acid very quickly protonates the OH of the alcohol group through that proton transfer, resulting in a really good leaving group and a good nucleophile, right? What we find is that methyl and primary alcohols react via an SN2 mechanism, right? And so let's look at an example of this. So methyl and primary react via an SN2. And so that's what we're going to look at here. So we have our happy primary alcohol, and we are going to add for this the HBr. And so the first step is a proton transfer, where the electrons on the oxygen come out and they grab the proton, and then these electrons go onto the bromine. When this occurs, we end up with that protonated alcohol, and then a really good nucleophile here is our bromine. And so what happens then is this goes through the backside of tack of an SN2 reaction, where the bromine comes and attacks the carbon attached to the leaving group because it's partially positive, and then this leaves as a water molecule. And now we have formed our alkyl halide and water as a byproduct. There we go. And water as a byproduct. Now, SN1, what we find is that Secondary and tertiary alcohols go through an SN1 mechanism. Now, when we look at an example of an SN1 mechanism, we're gonna do this with a tertiary alcohol, right? I want you to notice the first step, that proton transfer, is gonna be the same. Right, where we form a really good leaving group. So proton transfer, this is the same. Here is where we differ. We are going to undergo heterolysis here because it's a SN1 mechanism. So that water is going to leave as the leaving group. So we undergo heterolysis and we form a carbocation. Then the bromine, right, comes along and coordinates to that right here, and we form our alkyl halide. Now, a few notes about this, okay? First thing, both the SN2 and SN1 begin with the same step. It's a protonation step here through that proton transfer. Right? And that forms a good leaving group, and then both mechanisms give an alkyl halide here, here, and here as the products. Now, the mechanisms differ in the timing of both the bond making and breaking, okay? Now, knowing the mechanism also allows us to predict the stereochemistry of the products when the reaction occurs at a stereogenic center. And so, if we are at a stereogenic center, so if you are going through an SN2 reaction and you are at a stereogenic center, it's important to remember that inversion occurs. This means if you start with R, then you're going to end up with S. Okay, so that's something to be aware of. Then secondary and tertiary react by an SN1 mechanism. So if you have a stereogenic center, then you are going to end up with racemization. So all the rules for SN2 and SN1 that we learned in a previous chapter still apply here. Now, let's look at the alkyl halide reactivity in reactions like this. Well, dear students, I gave you a slide to do the SN1 and SN2 mechanisms with alcohols right here, and I got so excited about them, I did them on the previous slide. So, I'm going to skip on and now talk about the reactivity of hydrogen halides. So, what we find here with our hydrogen halides is the reactivity, right, increases with increasing acidity. Right? So what we find here is that CO- is a poorer nucleophile than Br minus or I minus. Okay. Now, because of this, right, a reaction of a primary alcohol with HCl occurs only when a Lewis acid catalyst, generally zinc chloride, is added, right? And so what we see here is that we have our, let's say, primary alcohol, like this, and then we have zinc chloride. The electrons of the primary alcohol are going to come out and they're going to make a complex with that zinc. Okay, so they're going to coordinate there. And when this occurs, now this reaction goes through that SN2 reaction, where the electrons on the chlorine are going to come and attack the carbon of the leaving group because it's partially positive, and then this is going to leave. Now, I forgot a charge, so don't be me. There's a positive charge there, okay? And so that leaves. Now, that complexation of the zinc chloride with the oxygen atom of the alcohol makes this now a very good leaving group, and that's what facilitates the SN2 reaction. So we end up with our alkyl halide, and then the leaving group here as well. Okay, but the alkyl halide is kind of the star of this reaction. Now, another way to convert alcohols to alkyl halide, right, is by using thionyl chloride. Okay, so we find that primary and secondary alkyl halides can be converted to, alcohols, primary and secondary alcohols can be converted to alkyl halides using either thionyl chloride or phosphorus tribromide. And we're going to look at both of those. We're just going to start with the thionyl chloride, which is SOCl2. So this is thionyl chloride. Okay. Now, thionyl chloride is going to convert the OH into a really good leaving group in situ. And that means directly in the reaction mixture. And it's also going to provide the nucleophile to displace the leaving group. So let's look at this mechanism of the reaction of the alcohol with the thionyl chloride. So I'm going to start with a generic alcohol for this mechanism. And then when I draw my thionyl chloride, there's a sulfur with a double bond and oxygen, and then the two chlorines here, okay? Now, here's the deal. These chlorines are electronegative, this oxygen's electronegative, we're withdrawing all sorts of electron density. That makes this sulfur partially positive. And so we have electrons on this oxygen, that sulfur's partially positive. These electrons come here and they attack that sulfur. And when they do, a chlorine leaves. This forms a complex where that alcohol now is protonated. And then pyridine comes in. And it steals that proton, and those electrons go onto the oxygen. And so we follow our arrows where, and now the nucleophile is going to come in. And remember, this is really withdrawing electrons, so that makes that carbon partially positive. So the nucleophile is going to come in, it's going to attack that partially positive carbon. These electrons are going to jump here to make a double bond, and when they do, this chlorine leaves. Okay, now that's an SN2 reaction, and we form our alkyl halide and sulfur dioxide, and then we also end up with Cl-. But the alkyl halide is the thing that we're most interested in here. Now, let's look at phosphorus tribromide. Phosphorus tribromide is another way to convert alcohols to alkyl halides, specifically primary and secondary alcohols into primary and secondary alkyl halides. Now, let's look at this mechanism. Again, I'm going to start with my generic alcohol. And when we see phosphorus tribromide, we have the same kind of issue going on. We have bromines, which are really electronegative, and they're going to withdraw electron density, and that makes this partially positive. And so when that occurs, the electrons on the oxygen are going to come over here, and they're going to attack that phosphorus. When they attack that phosphorus, one of the bromines leaves. Now, we follow our arrows and we see that oxygen, there's a new oxygen phosphorus bond. We still have our hydrogen, and now we have a positive charge there. And that, of course, is going to make the oxygen a better leaving group. Okay? And so now we have our nucleophilic attack, where the bromine is going to come in and attack that partially positive carbon, and the oxygen is going to leave. So this is our SN2 reaction. And now we formed our alkyl halide and that molecule as well. Now, I love a good summary, right? And so I love how this is summarized here. If you want to convert an alcohol to an alkyl halide with a chloride group, the reagents that are good are HCl, and the mechanism it proceeds by is an SN1 mechanism for secondary and tertiary, and an SN2 mechanism for a methyl alcohol and primary. Okay, and that's really useful for all alcohol types. If you use thionyl chloride, that is best for methyl, primary, and secondary, and it proceeds by an SN2 mechanism. Doesn't work well for tertiary, because remember, tertiary reactions, tertiary alcohols will have too much steric hindrance for an SN2 reaction to occur. If you want to convert an alcohol to a bromine, alkyl halide with a bromine here, HBr, useful for all alcohols, right? SN1 mechanism for secondary and tertiary, SN2 for methyl and primary. If you use PBr3, it's best for methyl, primary, and secondary. It's an SN2 mechanism. So SN2 mechanisms don't work with tertiary alcohols because there's too much steric hindrance. So don't forget that. Then, if you want to convert to iodine, an alkyl halide with iodine here, and you're going to use HI. This is useful for all alcohols, whether they're secondary and tertiary, occurring by the SN1 mechanism, or methyl and primary, occurring by the SN2 mechanism. So this ends for us our screencast on the conversion of alcohols to alkyl halides, as well as a little bit of dabbling into forming alkenes from alcohols. If you have any questions, please feel free to stop by my office.